Welcome to my talk about distance computation in the hybrid model via Oracle simulation. My name is Volodymyr Polosukhin, and this work is done together with Dean Leitersdorf and Professor Keren Sensor-Hillel. Hybrid networks are all around us. Consider, for example, a hybrid dataset which contains both electrical network and optical network. Another interesting example is smartphones with short-range device-to-device communication and all-to-all communication via cellular infrastructure. Augustin et al. Recently introduced a theoretical model which captures various hybrid networks. This is a distributed communication network, and the network here is given as a graph. Each node in the graph has a processor in it to do computations. Initially, each node knows its adjacent edges. Communication between some pairs of nodes occurs in synchronous rounds, and the complexity metric is the number of rounds till the last node terminates. In this recently introduced hybrid network model, nodes communicate via local and global communication graphs. The local communication graph coincides with the input graph, and each pair is connected with an edge of unbounded bandwidth, which means that in each round, every pair of nodes connected with an edge can exchange an unlimited number of messages. The global communication graph is click, and in one round, each node can send and receive order of log n messages of order of log n bits long. Those familiar with the fields can recognize that this model is a combination of the classical local model and recently introduced node-capacitated click model. For different combinations of local and global bandwidths, this model captures another established models, like local, congested click, or node-capacitated click. In this paper, we improve upon the state-of-the-art results for distance computation approximation. First, we focus on distances from multiple sources. In the multiple source shortest path problem, each node is given adjacent edges and an indicator of whether it belongs to the set of sources or no. And each node is required to compute its distance to each one of the sources. We show how to compute an exact weighted shortest path distance from n to the third sources in roughly n to the third rounds. All our results are randomized and held with high probability. This result improves upon the previous known result for single source shortest path in n to 2/5 rounds with high probability both in round complexity and in the number of sources. We also show how to approximate distances from n to the x sources in roughly n to the third plus n to the x divided by 2 rounds. This is optimal up to polylogarithmic factor due to lower bound Kuhn-Schneider show for number of sources which is greater than n to 2/3. Those results are based to the solution to the problem we call n to 2/3 RSSP. In this problem, each node is included in the set of sources with probability n to minus third. So there are roughly n to 2/3 nodes with high probability, and this is where the notation comes from. So we show an algorithm which compute an exact distances from set of sources sampled with probability n to minus third in roughly n to the third rounds. This is tied up to a polylogarithmic factor due to lower bound we show, which is a modification of the lower bound technique introduced by Augustin et al. This also improves upon results given implicitly by Kuhn-Schneider. In addition, we show 1 plus epsilon unweighted and 3 weighted approximations for eccentricities, as well as 1 plus epsilon unweighted and 2 weighted approximations for diameter in roughly n to the third rounds. The eccentricity of some node is the distance from that node to the farthest node from it. And the diameter is the maximum eccentricity. Basically, the largest distance in the graph. Our results for diameter improve upon the results from the previous work both either in round complexity or in approximation factor. And they also compare nicely with the lower bound shown by Kuhn and Schneider for exact diameter and 2 minus epsilon weighted diameter. Those problems require roughly n to the third rounds. One thing which is more interesting and important than the results is the communication primitives we show. We encapsulate those primitives by simulating some powerful model over some overlay graph we introduce later. The first model is Oracle. There is a node which sends DEGV messages to and receives DEGV messages from each node V in single round. Basically, this model allows to learn the entire graph in the single round. And another model we introduced is tiered oracles. There, basically, each node can send the set of DEGV messages to all nodes with a higher degree. This allows us to bin nodes into the bin according to degree and learn by the nodes from higher degrees the entire graphs of the lower degrees. It is too expensive to simulate those models over the entire graph. That is why we simulate them over the skeleton graph, which I'm going to define later. The key for our simulation results is density awareness. Basically, we use the fact that nodes in denser neighborhood have more access to global edges. In this slide, you can see the connection between different results. In a warm-up path, we show how to simulate an oracle. We use it to solve an exact single source shortest path problem. And this immediately implies two approximation for weighted diameter. In the bottom path, we show how to simulate tiered oracles. Then we use this simulation to compute exact distances from sources sampled with probability n to minus third. And these results allow us to compute exact distances from given set of n to the third nodes, approximate distances from given set of n to third sources, compute 3 approximate weighted and 1 plus epsilon approximate unweighted eccentricities. And the eccentricities result lead us to 1 plus epsilon approximate unweighted diameter. All those algorithms require roughly n to the third rounds. As I mentioned before, it is quite slow to simulate powerful models over the entire input graph. That is why we simulate oracle and tiered oracles over the skeleton graph. To obtain the skeleton graph, we sample each node with probability n to minus third. Then we connect closed skeleton nodes, sampled nodes, with those nodes with distance n to the third times some polylog with an edge. Throughout the slides, h is going to denote the distance, basically the n to the third times some polylog required for our properties to hold with high probability. The graph we obtained have a bunch of useful properties. The most important distance property previous works show and use is the fact that between any pair of nodes on distance greater than h, greater than roughly n to the third, there is a skeleton node on some shortest path between them, each roughly n to the third nodes. We are not the first to simulate powerful models over the skeleton graph. Kuhn and Schneider show how to simulate one round of the congested clique model in roughly n to the third round. In this congested clique model, each pair of nodes in each round can exchange one message. We find also useful to simulate the one round of the local model over the skeleton graph, and it is clearly could be done in roughly n to the third rounds using the local edges of the hybrid model. So the more interesting model we can simulate on the skeleton graph is the oracle. Recall that in this model, on each round, there is a node which sends and receives to and from each node V DEC-V messages. We show how to simulate one round of the oracle over the skeleton graph in roughly entry-sort rounds. To simulate this model, we use the simulations of the congested click and local model I talked about before. So first we select this, the oracle as the node with the maximum degree in the skeleton graph. Notice that the degree here is correlated with the density of the neighborhood. Hence, it's also correlated to the access of the node to the global edges. And then we use the congested click model so that each skeleton nodes sends at most one message to each one of the neighbors of the oracle. Finally, we use the simulation of the local model over the skeleton graph to learn by the oracle the messages from its neighbors, which it received. Now, our first warm-up distance result. It is the exact weighted single source shortest path in roughly entry-sort rounds. And it follows directly from the oracle simulation. First, we build a skeleton graph and let the oracle learn it and compute the exact single source shortest path on this skeleton graph. Then oracle informs each skeleton about its distance from the source. And finally, we extend the single source shortest path result from the skeleton graph to the entire graph, doing some local explorations. Immediate corollary from our single source shortest path result is to approximate diameter in the same roughly entry-sort rounds. It compares nicely to the lower bound of entry-sort rounds for 2 minus epsilon approximation of the diameter shown by Kuhn and Schneider. In the oracle model, we pretty much exploited the entire sending potential of each node, unicast potential. However, each node may send more messages with multicasts. Recall that in the tiered oracle model, each node has a set of DEC-V messages, and in one round it sends those messages to all the nodes with the degrees higher than the degree of this node. We show how to simulate one round of the tiered oracles in roughly entry-sort rounds of the hybrid model. To simulate it over the skeleton graph, we first use congested click simulation to send each message to as many random nodes as we can in per logarithmic number of congested click rounds. Then we use the simulation of the local model over the skeleton graph, and each node eavesdrops to the messages its neighbors received. So notice that the nodes from denser neighborhoods, nodes with larger degree in the skeleton graph, receive more messages. Consider the problem of computing shortest path from sources sampled independently with probability n to minus third. There are roughly n to 2/3 nodes with high probability. And the main reason we consider this problem is that the solution of it leads to the solution of other more classical problems like computing distances from multiple given sources. Kuhn and Schneider implicitly approximate the solution for this problem by simulating fast approximate shortest path algorithms from the congested click model over the skeleton graph. We solve it exactly using the dedicated tiered oracles algorithm in roughly entry-sort rounds of the hybrid model. First, we build a skeleton graph and bin its nodes into log size of the skeleton graph tiers according to their degree in the skeleton graph. Then we use tiered oracles model to send the incident edges of each node to all the nodes from the tiers above. Then we start from, Then we start from uppermost tier, and in this tier, nodes know the entire graph. So they can compute distance from themselves to all the nodes in lower tiers. Then they use one round of the congested click module to inform each node from the lower tiers about the distance from itself. For next tiers we proceed. The nodes there already know the distance from all the nodes in the tiers above, and they aim to compute their distances from themselves to the nodes in the same tier or below. Let's take a look at the picture in the right. The node U already knows the distances from all the upper tiers, and for some node U prime below, from the tiers below, the path from U to U prime either passes entirely via nodes in the same or lower tiers, or it passes via some nodes in the upper tiers. In this case, let's take a look at the W, the last node from the upper tiers on this path. U knows the distance UW, and U also knows all the edges on the shortest path from W to U prime, because at least one of edge points reported it to you. So basically you can compute its distance to U prime. We use a lower bound technique for the hybrid model introduced by Augustin et al. And applied by Kuhn and Schneider for MSSP, and applied in our case for SSP, and shows that our result for shortest path sampled with probability n to minus third is tight after to logarithmic factor. Now we use the aforementioned algorithm to compute exact distances from n to the third given sources in roughly n to the third rounds. Notice that this improves upon our warm-up result for single source shortest path in terms of number of rounds. We start by building a skeleton graph and computing RSSP from the set of skeleton nodes. Then each source node we branch according to the density of its neighborhood, which is correlated to the number of skeleton nodes in its neighborhood. We aim for each skeleton node to learn the distance from this source. Then this will allow us for all the nodes to compute the distances to this source using the properties of the skeleton graph. If in the n to the third hop neighborhood of some source there are not many skeleton neighbors, at most roughly n to the third, we can use a token dissemination routine developed by Augustin et al. To broadcast distances to each one of the skeletons. Otherwise, if there are more skeleton nodes, then we sample one of them to assist us and use congested click to send distances from the source to each one of the skeletons via this intermediate assistant node. Finally, we use the properties of the skeleton graph to compute the distances from skeletons to each one of the sources, and then from all nodes to each one of the sources. Over with our exact results. Now let's discuss our approximate results. First, we show how to approximate paths from n to the x given nodes in roughly n to the third plus n to the x divided by 2. As you may guess, we start by computing an exact n-to-2 sorts SSP. Then each node selects its representative, the closest skeleton node to it. We use token dissemination protocol to inform all nodes about each source representative and distance to it. And finally, for each node, it approximated the distance to the source by taking a look at its n to the third hop neighborhood or traveling via the representative node. The token dissemination step here takes n to the x divided by 2 rounds. Other steps require n to the third rounds. Hence, we obtain our claimed round complexity, and this round complexity is tied up to logarithmic factor for more than n to the 2/3 nodes. Recall that the eccentricity of some node is its distance to the farthest node from it, and the diameter is the largest eccentricity, hence the largest distance in the graph. We show how to approximate in roughly n to the third rounds the eccentricity and diameter for unweighted graphs. We again begin by solving an exact n to 2/3 SSP. Then we approximate each eccentricity as the distance to the farthest node in the n to the third hop neighborhood or the distance to the farthest skeleton. Finally, we approximate the diameter as the largest eccentricity. The trick from the previous slide won't work for computing weight eccentricities, as in the proximity of some skeleton nodes there may be a very heavy edge, which breaks the approximation factor. In order to fix this problem, each skeleton node disseminates the distance to the farthest node in its roughly n to the third hop neighborhood. Then each node approximates its eccentricity as the maximum over the sum of distances to the skeleton node and the farthest node nearby that skeleton node. This leads to approximation factor of 3 in roughly n to the third rounds. Okay, so let's summarize. In this work, we show how to simulate powerful oracle and tiered oracles over the skeleton graph in recently introduced hybrid network model. We improve upon the state-of-the-art algorithms for distance computations. Our main technique is density awareness. We exploit the fact that nodes in the denser neighborhoods receive more information using global edges. Thank you for your attention.